Being able to perform a phonological analysis on an unfamiliar language is one of the key concepts in an introductory linguistics course. This short movie is intended to walk you, step by step, through the procedures of phonological analysis. The example used here is from the Cameroonian language Kenyang, but the logical process is applicable to the analysis of any language. Before getting started, orient yourself to the problem and the dataset. The introduction will usually tell you some basic information about the language and might give you a clue about what to focus on. The introduction to the Kenyang dataset says, Kenyang is a Niger-Congo language spoken in Cameroon. The data below feature voiceless stops in this language. Consider this data, then answer the questions that follow. Note, k is a voiceless uvular stop and ch is an affricate, not a stop fricative sequence. Next, take a brief moment to look over the dataset. Try to identify the phones which may be of interest. The introduction stated that the focus here is on voiceless stops, so taking a quick mental inventory of the voiceless stops is a good strategy at this point. Now that you've acquainted yourself with the dataset and have a good idea of what you'll be looking at, you can start answering the questions. Question 1 asks, is the distribution of k and k complementary or contrastive? You should note at this point that both k and k are voiceless stops with different places of articulation, which you have already identified visually in the dataset. This question is asking you to determine the type of distribution that these phones have, only on the basis of the dataset provided. For small datasets, it's usually quite a bit faster to determine if the distribution is contrastive, because determining complementary distribution, as we'll see, requires a bit more work. You can be 100% certain that the distribution of any two phones is contrastive if you can find a minimal pair for those phones. If the distribution of k and k is contrastive, you should be able to find two words whose only difference is that one has the voiceless velar stop where the other has the voiceless uvular stop, and which have different meanings. Study the dataset carefully. Is there a minimal pair for these two phones? No. There are no two words with different meanings, such that one has k where the other has k. This means that the distribution is definitely not contrastive. So at this point, we are leaning heavily towards answering complementary for question 1. But just because the distribution is not contrastive does not automatically mean that it is complementary. The phones might be in free variation, which would mean that they do not contrast meaning, but also do not occur in predictable environments. In order to be certain that the distribution is complementary, it is crucial to identify some phonetic environment in which one phone always occurs and in which the other phone never occurs. In other words, the surrounding phonetic environment for each phone must never be the same. One easy way of assessing the phonetic environment for each phone is by making T-tables. T-tables are little charts which show the phone or word position both preceding and following the phones in question. When making T-tables, it is imperative to go through the dataset carefully and systematically to reduce the likelihood of error. Let's start with the T-table for the voiceless velar stop. The first voiceless velar stop in the dataset is in data point 2. The phone preceding it is the vowel A, so this vowel goes to the left of the vertical line. Following the velar stop is not a phone at all, because the velar stop is the last phone in this word. So to the right of the vertical line, we can put a hash mark, which is the notational symbol for word boundary. We have now indicated that the voiceless velar comes after the vowel A and before a word boundary. As we carefully proceed through the dataset, we mark the preceding and following environments for every instance of the phone in question. Then, once all the voiceless velar stop environments are indicated on the T-table, we can repeat the entire process for the other phone in question, the voiceless uvular stop. Now that we have identified the surrounding environments for each phone, we can easily determine if any of these environments is shared by the two phones. Does the velar stop ever occur in an environment where the uvular occurs? No, the surrounding environment is different in both cases. Does the uvular stop ever occur in an environment where the velar occurs? No, the surrounding environment is different in both cases. Since the two phones never have the same surrounding phonetic environment, it must be the case that they are in complementary distribution. And that is the answer to question 1. But before moving on to other questions, it is important to make sure that you understand what this actually means. If the distribution is complementary, then the phones are allophones of the same phoneme. The phoneme is realized as one allophone or the other, depending on the surrounding phonetic environment. We can represent this fact of Kenyang mental grammar visually, with diagrams that show the relationship between phonemes and allophones. The situation in Kenyang is like this. The phoneme has two allophones. It is not like this, where each phone corresponds to its own phoneme. A little later, we'll return to this concept to figure out how to decide which of the two allophones should represent the phoneme. Let's move on to question 2. Question 2 asks, if the distribution is complementary, what is the environment that conditions each allophone? If the distribution is contrastive, what evidence in the data supports this conclusion? We have already determined that the distribution is complementary, so we only have to figure out the conditioning environment for each allophone. Luckily, we have done most of the work already. Let's take another look at our t-tables. It is important that we are careful to look at both sides of the t-table for each phone to determine the relevant phonetic environment. Starting with the environment preceding k, we can ask, do these phones form a natural class? In other words, what phonetic property do they all have in common? They are all front vowels. Now look at the environment following k. Do these form a natural class? Well, no. They cannot form a natural class because they are not all phones. Some of them are vowels, but the rest are word boundary symbols, which are not phones. So these segments do not have anything in common. Now look at the environment preceding the uvular stop. Do these form a natural class? Yes, they are all back vowels. What about the environment following k? Again, these are not phones, so they cannot be said to form a natural class. But they do all have something in common, which is that they are all word boundaries. So k always comes between a back vowel and the end of a word. The answer to question 2 is a statement which summarizes the consistent environments for the velar and uvular stops. The allophone k occurs after front vowels, and the allophone k occurs word finally after back vowels. Question 3 asks, which of the two allophones probably represents the phoneme? At this point, we can return to the issue posed earlier about how to represent the phoneme. Between the two allophones, how do we decide which one should represent the phoneme? One straightforward way of doing this is to determine which allophone occurs in a less restricted phonetic environment. The allophone with fewer restrictions is, in theory, the one which speakers of the language treat as basic or default in their mental grammars. It is the one which is used in every environment where it could occur, except for the environment of the other allophone. Sometimes this default allophone is also called the elsewhere case, because one allophone is used in a very specific environment and the other one is used elsewhere. So, which of the two allophones has a less restricted phonetic environment? The velar stop exists between a vowel and a word boundary. That is one environment. It also exists between two vowels. That is another environment. So there are at least two types of environments in which k occurs. The uvular stop, on the other hand, only exists between a vowel and a word boundary. There is only one type of environment in which occurs. This means that the environment for the uvular stop is very restricted. There is only one. The environment for the velar stop is less restricted because it occurs in more environments than the uvular. Therefore, we will select the velar stop to represent the phoneme. The mental grammar of Kenyang speakers is therefore like this, and not like this. Question 4. Using rule notation, write a phonological rule to account for the observed distribution of k and q. Recall the template for phonological rules. Identify a natural class of the phoneme and present this as the starting point for the rule. Then, identify which phonological features or properties the more restricted allophone has, which the less restricted one does not. Present these following the transition arrow in the rule. The slash represents a statement specifying a phonetic environment. And finally, the phonetic environment which conditions the more restricted allophone is listed using an underscore to position the phone which undergoes change. In the Kenyang example, a voiceless velar stop becomes uvular when it occurs after a back vowel and before a word boundary. There are a number of other ways a phonological rule could be formulated for the Kenyang data we have seen. The rule is often still accurate when certain phonological properties are omitted. For instance, the original rule starts with voiceless velar stop. But removing voiceless does not affect the accuracy of the rule because there is nothing in the data contradicting the claim that all velars become uvular in that environment. Note that we do not have positive evidence from the dataset that this happens to voiced velars, but we would like our rule to be as general as possible. It would be easy to amend the rule later if additional data suggests we should. Another possible rule is one which omits the final word boundary. As far as we can tell from the dataset, voiceless velars become uvular anytime they occur after back vowels. There is nothing in the data to contradict that claim. However, it is important to be careful not to formulate your rule such that something in the dataset actually does contradict it. For instance, we could not have a rule stating that voiceless velar stops become uvular before word boundaries because there is a word in the dataset, item 2, which contains a voiceless velar stop before a word boundary. This rule would predict that final velar to become uvular, but since that is not what happens, the rule cannot be correct. Question 5 asks, does the observed distribution make sense from a phonetic perspective? This question is trying to get you to see the relationship between the anatomical or articulatory facts which are described in phonetic terms and the psychological or mental propositions which are described in phonological terms. Think about the places of articulation of the two allophones. The allophone k is produced at the velum, while q is produced at the uvula. Notice that the velum is further forward in the oral cavity than the uvula is. Now think about the environment in which each allophone occurs. The velar stop is always preceded by front vowels. The uvular stop is always preceded by back vowels. Front vowels are produced further forward in the oral cavity than back vowels are. So the fact that velars come after front vowels and uvulars come after back vowels is not surprising. It makes good sense from a phonetic perspective. What is probably happening here is a type of assimilation. The phoneme of the voiceless velar stop moves further back in the mouth when it is produced after a back vowel, because back vowels are produced further back in the mouth. That same phoneme is realized at its usual place of articulation at the velum when it is produced after a front vowel. Moving on to question 6. Is the distribution of aw and o complementary or contrastive? This question is the same as question 1, except that it is asking about the phones aw and o instead of the phones k and q. So we can use exactly the same strategy as we did for question 1. The first thing we want to do is try to find a minimal pair. Can we find any two words with different meanings such that one has aw where the other has o? In fact, there are two such words in the dataset. Numbers 1 and 4 meet the qualifications for a minimal pair. Since we have found a minimal pair for these two phones, we can conclude immediately that aw and o are in contrastive distribution. Now, question 7 asks, if the distribution is complementary, what is the environment that conditions each allophone? If the distribution is contrastive, what evidence in the data supports this conclusion? We decided that the distribution is contrastive, and the evidence for this is the minimal pair that we discovered in the dataset. To answer this question, we can just state this explicitly. There is a minimal pair in the dataset, Enoch, tree, and Enoch, drum. Since aw and o are the only differences between these two words, these phones are the only things which allow speakers to distinguish between them. Therefore, they contrast word meaning. Again, it's important to understand what this means in terms of the phonological system of Kenyang. Since the phones are in contrastive distribution, it is impossible to predict which phone will occur simply by looking at the surrounding phonetic environment. That is because there is no phonetic environment which conditions these phones. They each belong to different phonemes. That means that the mental grammar of Kenyang speakers is like this, and not like this. And that is how to perform a phonological analysis. After reflecting on this procedure, some of you may be thinking, why should anyone care? And assuming this question comes from a genuine place, it's a very important question to ask. It's easy to get bogged down by the details of such an analysis and lose sight of the bigger picture. In justifying something like this, it is often helpful to distinguish between its theoretical significance and its practical significance, and depending on your personal interests and goals, one of these may demand a greater emphasis, but they are certainly not unrelated. In a broad theoretical sense, one of the objectives of the field of phonology is to characterize the relationship between sound systems as they exist in our brains and actual speech as it comes out of our faces. A phonological analysis of the kind we have just done is a major contributor to that endeavor because it allows us to postulate the existence of specific psychological entities on the basis of physical, acoustic evidence in the real world. On the practical side, the type of information that we obtain from such an analysis can be used to aid our understanding and treatment of real-world problems, such as speech disorders, first and second language learning, and the acquisition of literacy. It is important to keep these things in mind even as we toil over minute details of a particular dataset. Furthermore, for some people, it is easy to fall into a trap of dismissing a language like Kenyang as obscure or insignificant with little import for understanding the so-called major languages. In fact, there is nothing particularly special about Kenyang. It is one language out of thousands, and each of these languages displays allophonic variation. But this means that Kenyang is just as good of an example as, say, German for understanding the common properties of human language, even though it has less than 0.1% as many speakers as German, and most Westerners have never heard of it. In fact, German displays exactly the same kind of allophonic variation we have seen in Kenyang. Front vowels condition allophones further forward in the oral cavity, and back vowels condition allophones further back in the oral cavity. And this is significant because it means that human vocal tract anatomy, which is largely the same for everyone, tends to have the same kinds of effects on mental grammars, even though the specific details of those grammars may be quite different. This is not something we could ever discover by restricting our investigation to the languages of Europe, for instance, or languages with over 1 million speakers. But when we treat all languages as equal representatives of the human capacity for language, we start to see some of the phenomena that truly unite us.